Thanks, Thomas. So the work that I'm going to be talking about today the main part of it is actually out. It was done in collaboration with Ian Moss and Ben Withers. And there's another paper which I think we were just lamenting over lunch, that you get within epsilon of finishing a paper and then somehow that last bit, it's Zeno's paradox, you never quite get to the point. Anyway, it should be out soon with my student Philip Berder. And so hopefully it says to appear, and hopefully it will soon. So just as an outline, I'm going to just very briefly review the Coleman-Delizia calculations. So these were done over a period of 5 years or so in the late 70s and early 80s. And it started off as a calculation in field theory and ends up as a calculation in Euclidean gravity. So I'll just go over that. And then I'll talk about what we did last year in generalizing Coleman-Delizia. So the basic story is that we're going to again take these general relativistic instantons and add in black holes to the mix. So I'll describe, it's very short description about generalizing the picture of Coleman-Delizia, but there's a sort of little technical bit in there. That's really the technical result of that paper I mentioned, which is discussing singular instantons and how to properly compute the action in that case. Then I'll describe what happens when you catalyze a tunneling process with a black hole, and sort of say how CDL is changed. And then finally I'll just mention what's hopefully coming out soon is where we're applying this to the Higgs vacuum. So the question is, what's the issue? The issue is that Coleman and Delizia started this, I think at the time, gravity was quite confined to sort of fairly specific scenarios and was very much used classically. And so obviously during the 70s, people were beginning to get more adventurous with exploring quantum ideas in gravity. But this idea of doing something non-perturbative, the instantons, I think really began to mature with Coleman-Delizia, because it wasn't just purely gravity, it was actually beginning to look at more complex scenarios. So you've not just got gravity, you've also got field theory, and everything's sort of non-linear. But still you can do analytic stuff. So it's certainly true that Coleman-Delizia is the gold standard in calculating these tunneling decay rates, but I think the question that we were interested in was how dependent was that picture on homogeneity, because as you'll see, Coleman-Delizia is very, very specialized. And so this was the image I had. Well, actually not specifically this image. The image I had was, I spent quite a few months a year at Perimeter Institute in Canada, so when you're at 110 volts, you don't tend to heat water up in a kettle because it takes too long. You shove it in your mug in the microwave and boil your water that way. So you pick your mug out of the microwave, put something in it, and poof, it would suddenly fizz. So it was that notion of adding something, adding an impurity, catalyzing a phase transition, and of course, so that was really where it started. And of course, the biggest impurity in gravity is a black hole. So here's just a brief review of the work of Coleman and Delizia. It actually started, this is a sequence of 3 papers, which starts with a paper by Coleman in 77, where he considered decay of the false vacuum in field theory. So the picture is there a pointer or something approximated? I can't use my, I'm slow enough. So the notion is that we have 2 local minima in some potential, and but one is just a tiny bit, teensy bit, in epsilon lower, thanks, than the other one. And so in this circumstance, we would expect that if we started off quantizing around this vacuum, that this vacuum would only be metastable, and that it could decay down into what we call the true vacuum. And so the picture here is you've got an initially homogeneous state of false vacuum, and inside nucleates a bubble of true vacuum. Now this wall is where the field sort of this can be a classical configuration, and the wall is where the field goes up and over the potential barrier into the true vacuum. And so that's very nearly what we know from topological defect theory as a domain wall, and it tends to be quite thin, and it carries energy momentum. And so Coleman estimated the action by saying, well, you know, the picture is that you get this bubble that just spontaneously appears. If it's too small, the energy of the wall, it costs too much energy to make the wall, more energy than you'll gain from jumping to the true vacuum in the middle, and so the bubble will just recollapse. If it's too big, yes, you've got more energy by making more of your space true vacuum, but then, you know, it costs a lot more because you've made a huge region change from one vacuum to the other. And so you kind of put those two features in, the volume factor with the potential energy difference epsilon, and the area of the wall factor with the what we call sigma, which is the energy per unit area of the wall. And so r is the radius of the wall, and you kind of look for the stationary point, and you pop that in and you calculate the action, and you get this characteristic dependence on the tension of the wall and the energy difference between the true and false vacuum. And so the tunneling amplitude would then be, at least to leading order, e to the minus this bounce action, as it's called, over Hbar. So that's Coleman's picture, and it's you know, that's a very intuitive way of doing it. But of course you could then calculate the Euclidean field theory solution, and it would correspond to this picture pretty well. The Delizia bit is adding in gravity. Now, in this case, the instanton is just like you construct these tunneling solutions by rotating. It's sort of a trick. You go to Euclidean time and look for a sort of classical Euclidean solution. You do that here with Einstein equations. You look for Euclidean Einstein solutions. And in this case, the picture is, well, if you're in false vacuum, that would be a positive energy density, so that's de Sitter space, positive cosmological constant. And then flat space is the true vacuum, that's the absolute minimum. And so you're looking for a bubble of flat space inside de Sitter space, separated by some thin wall which has some energy momentum. And the key difference between the Coleman calculation and the gravitational Coleman-Delizia calculation is that the wall radius is determined by your gravitational equations. So they're called Israel junction conditions, but it's basically, you do Einstein equations, your source is the wall, which is like a delta function, you've got a lambda outside, no lambda inside, you just solve the Einstein equations with this delta function. And that's actually gives you the radius of the wall. And so then your bounce action is uniquely specified because you found the full solution. And so here you get what is now a gravitational action, and you find to leading order it's still got this same sort of behavior, but of course now there's some G newtons floating around, and actually the denominator looks a little different, but it's very similar. So in terms of geometry, we're dealing with general relativity, so that's just differential geometry. What does it look like? Well, you can actually draw the Coleman-Delizia instanton because it's a Euclidean solution. De Sitter space, Euclidean de Sitter space, is just a sphere. It's a cosmological constant, positive cosmological constant. That's a constant curvature space, that's a sphere. Flat space is just flat, no sophistication there. And so this is what you've got. You've got a bit of a sphere, you've chopped off the end. This bit's flat, and round the edge there's a sort of, you know, ridge, a disconnect, kink in your geometry where you go from flat to curved, and that discontinuity is what gives you the delta function source that's the wall. Now, of course, in reality it'll be smooth, you can integrate out if you want in a given field theory, but this is a very good approximation to what the actual solution would be. So this is what it looks like, and This is just here, this is de Sitter space, it's a metric of a force sphere in this case, and that has a particular gravitational action. You get a truncation radius from your equations of motion, and then you bung all that in. And when you put things back in terms of the various parameters, L is the radius of curvature of the de Sitter space, which is related to that energy difference. This sigma is the tension of the wall, but it's got a 2 pi g in it, so it's like, you know, you're sort of taking, there's a Newton's constant hidden away in here. This is what I meant by the denominator being altered a little. And then, of course, you should expect to see a g sort of proudly displaying itself in there, because this is, after all, a gravitational action. So that's the Coleman and Delizia action that they found.
Does it recover the flat space?
Yeah, so as g goes to 0, you kind of, well, first of all, this bit has got a g in it, so that'll go. And then, I know you've got a g up here, but these L's, L is related to lambda. Lambda is 8 pi g epsilon, okay? So you can see that here you've got an L to the 6 on the top. So L to the 6 is 1 over lambda cubed. So there's your 1 over epsilon cubed. Then you've got, that gives you a g cubed, plus this g on the bottom is 4 g's, which go with the 4 g's hiding in there. So it's all in there. It does go to the other. It's just perhaps the way this is written, it's not so obvious. You've kind of got to remember there's g's hiding in there and there's g's hiding in there. So, but it does, yeah. And then the picture of the overall decay process, or one possible picture, is that sometimes what you do is you cut this Euclidean instanton in half, sort of at a moment where it's time symmetric, so it's symmetric under reflection in the vertical axis, and you say, well, what happens below is the Euclidean quantum bit, and then you match it to a Lorentzian solution, which is just the analytically continued Euclidean solution. So a sphere in Euclidean terms becomes a hyperboloid in Lorentzian terms, and so this is this top bit is the expanding bubble. This here, you can see the amount of Minkowski space is growing, which is the interior of the bubble. And so this is often the picture of the full tunneling process. So one thing you should notice is just how symmetric it is. You know, the de Sitter space is this really symmetric sphere. You know, this bubble nucleates in a very symmetric way.
So the idea is nucleating.
And then once the bubble's there, it expands. So just like a normal bubble that you might expect.
What's the argument about the analog argument that you gave for the flat space, where if it's too small it won't?
Well, in that case, that's what the Israel conditions are doing for you for free, because they just won't match a smaller bubble or a bigger bubble. So it just doesn't fit together. So they kind of do it for free. Okay, so now it's time for a more general look. First of all, what could change? Well, if you think of the bubble as just one of these domain walls, if you ask what's a general wall solution, and this is, and actually I'm not sure if there is anyone in the audience who's worked on brane worlds. This was something that we did a lot when we did brane worlds. And if you're just looking for solutions to Einstein's equations corresponding to one of these walls, you can prove that the exact solution away from the wall is one of these generalized black holes. So you can see the 2gm and r bit, because we're in 4 dimensions in this case. So this is the integration constant. And in this case, I've explicitly written these down as functions of r, but you can prove this if they're functions of r and t. So there's, and the kappa just tells you about the curvature of that internal space. So the wall itself doesn't need this very symmetric space. It can have something with a little less symmetry. And it can separate regions with different cosmological constants and different masses for this black hole. So this is, from the wall's perspective, there's not a problem with stepping away from just pure de Sitter or purely flat space-time. And so when you try and sort of solve what's going on, you say, well, okay, I'm going to have a wall. It's going to be at some distance from the black hole, and you say, it's possibly time dependent, but you usually parameterize things by a proper time on the wall. And so you write down what the wall trajectory is. You use the Israel junction conditions. So this is just writing down what they are. It's just a statement about a jump in extrinsic curvature, the way the bubble is bending on each side. And then when you you go through the machinery, you find that what you get out is something that looks awfully like a Friedmann equation. This is why they were so popular in brain world cosmology, because this radius where the wall is satisfies, here we've got, this would be a flat universe, and there are these various source terms which depend on the tension of the wall and the geometry on each side. So Fbar is like an averaged Newtonian potential, and delta F is the difference in the Newtonian potential. So this is what the thing looks like. So an obvious question you could ask me, this isn't what Coleman and Delizia did, so what does that look like? What I've done, if you remember, was I wrote down a black hole solution. A black hole solution is always done in what we'd call a static patch, so the coordinates which are at rest relative to the black hole. Whereas Coleman and Delizia, and I could write, if I go back, to that, static patch, I could write de Sitter space. All I do to get de Sitter space is cross off 2gm on R, and in that case, I make kappa equal to 1, that's de Sitter space. But that's not a time-dependent cosmology, that's just de Sitter in a static patch. So that's what you have to do for Coleman and Delizia. This is de Sitter, this is Minkowski, and you have to go across the wall. Here's the 1 over r squared is the appropriate Friedmann piece for a positively curved universe, and you just get a constant on the other side. So you can see that for your for the Minkowski side, you're obviously just going to get trig functions, periodic functions, and then when you put everything in, and I see I haven't defined gamma, it's basically, this is gamma to the -2, you find that you've got these periodic functions. R is looking like a cosine, so the thing is kind of bouncing in and out, and the minus t, you've got a t minus and a t plus. So t plus is a bit more complicated, but that's what you've got. Now, the important thing to notice is the periodicity, the gamma in here, is not the same as the periodicity of the static patch. So it's if you Euclideanize the static patch, you've got a natural periodicity to have no singularities. That's not gamma, okay? So what that means is you're going to have a conical deficit in your bounce. So you need to be able to deal with conical deficits. Now they're very familiar if you're used to doing Euclidean gravity, because the first time that you meet one, typically, is if you're looking at Schwarzschild. So you Euclideanize Schwarzschild, you try and make it regular, you realize in general it may have a conical deficit, and then you adjust the periodicity of Euclidean time to get rid of that conical deficit, and that gives you the Hawking temperature of the black hole. Because no conical deficit, then the periodicity of your Euclidean time is 8 pi gm. So here, if you have Schwarzschild de Sitter, you cannot make both the cosmological and the black hole event horizons regular. So there's always a conical deficit for Schwarzschild de Sitter. So you're kind of used to them existing, but what happens? So here, the sort of ratio of the natural periodicities, unsurprisingly, are the ratio of the curvature of Schwarzschild de Sitter to the horizon scale of the black hole. That's the sort of magnitude of the problem, of the mismatch. So how do you deal with that? If you want to compute an action, you've got to deal with it. So we look at the conical deficit. There's a slight problem about, or you might worry about looking at these things, because what the Israel junction conditions do is they give you a way of dealing with a delta function in general relativity, and general relativity is highly nonlinear, so you might not expect delta functions to work. But if it's a delta function of just one direction, they do. However, here we're looking at possibly making a delta function in two directions. And there was a theorem by Gauss and Trashan from the early 80s which said you couldn't do this. However, the sort of information that you lose when you try and take a delta function limit is information that's both kind of mixing the two-dimensional space in which you've got the conical deficit with the rest of your space. And so it's to do with extra degrees of freedom which kind of correspond to the gravitational degrees of freedom that are sort of in the crosstalk. Whereas the type of deficits that we've got here are where you can cleanly split off your two-dimensional space with the deficit and the rest of the geometry, which is kind of just going along for the ride. It's just some constant, in this case, 2-sphere. So what we did was we smoothed out this A function. We're modeling the conical deficit by taking, here if it was flat, A squared would be rho squared. If it was conical, it would be 1 minus epsilon squared, rho squared, and so, delta here I've called it. And so we smooth out A such that A has derivative 1 at the origin and 1 minus delta at some epsilon outside the origin. The Ricci scalar, this is what you get in terms of these two functions, and because C is just a constant near rho equals 0, you end up seeing the delta function piece is sort of hidden away in A double primed on A. So you can extract the delta function piece and integrate it out. So you can integrate out root GR, and you find that the bit that you need is the deficit angle, or essentially the deficit angle times the area of the complement space. So that's what you get. And there's no information lost because there's no kind of cross-talking. That's the way I think of it anyway. So now we apply this to Schwarzschild de Sitter. So we, in fact, took an arbitrary periodicity, which means we've got conical deficits of both horizons. This would be the axis. Yep.
I have a question about degrees. Would
Yep.
it be the same as what Gauss is theorem, two dimensions E2, if you have conical difference, then integral of R is something?
I'm trying Gauss's theorem. I never know theorems by their names. It probably is. I think the only thing you have to know to be sure about doing it is to make sure that this doesn't mess you up. So you kind of need this to be a spectator. And that's so yes, probably it is, in the sense of, by looking at the higher dimensional Einstein equations, you isolate the fact that this is really, as you're going down to rho equals 0, this is a spectator, and there's nothing going on. So that obviously this result, it comes in here at this point, but it's along for the ride. So I bet you're right.
Integrating scalar curvature in 2 dimensions.
Yeah. Yes. Obviously, if you were just 2-dimensional, then you don't have the problem. The problem here, the problem that Gauss and Trashan found was actually in modes that were dealing with this part of the space-time and the way this part entwined with that. You notice there's no cross terms here. So but it's more than that. It is to do with the way the 4-dimensional Einstein equations split up, and in this case they are splitting up into 2. The bit that's singular. So yeah. So if you now just take a general periodicity, so you've got conical deficits at both horizons in Schwarzschild de Sitter, and then calculate all these pieces, what you find is these two terms, this term and this term and this term and this term, those are coming from the conical deficit. So I'm expressing the conical deficit as the difference between the natural periodicity, which would be this bit, and the periodicity that you've got, which is, so this is like the periodicity you've got divided by the natural one. So that's what you get from the conical deficits, and then you've got a volume term. Now the volume term, which is really coming from the lambda here, that obviously depends on the periodicity of Euclidean time. But if you work out, put in these natural periodicity values, you find that these two pieces are cancel out that piece. So I've actually put in what the betas are. So it's just one of those things where all the bits that would depend on whatever arbitrary periodicity you've chosen just fall out, and what you're left with is an expression which is purely in terms of the cosmological horizon and the black hole horizon radius. So this was kind of our first sign that this was a sensible thing to do, because we're now able to compute an action for a space-time that is independent of periodicity. So one of the things somebody could rightly complain about with conical deficits is, oh, but then how do you know that you can't change the periodicity to be whatever you like, and then you get a different action that's giving you different physics? Well, it doesn't work that way. So we were a bit surprised by that, but maybe someone else knows about it. Anyway, back to the walls and back to the bounce. That's dealt with dealing with the, yep.
Does it not happen in white space without the cosmological constant?
Why does what? Sorry?
For Euclidean Schwarzschild, for example.
But the thing with Euclidean Schwarzschild is you can make that regular. So when you're calculating the action of Euclidean Schwarzschild, you would never dream to put in an arbitrary periodicity, because an arbitrary periodicity would make the event horizon have a conical deficit. So you always compute it at the natural periodicity. So no, that's really, it's kind of weird. When we do, so we have had to do this to do more general bounce actions. So it looks, at first pass, it looks like that this arbitrary periodicity term might come in with Euclidean Schwarzschild, but when you calculate the bounce action and you start having to sort of subtract off all the different terms from inside and outside, any term that ever depends on an arbitrary periodicity for these solutions always falls out. So it's kind of one of those, I don't know, it just does. I wish, I don't know if there's any deeper reason for it. All I can say is, in this case, the cancellation is transparent. And in other cases, the cancellation happens when you're actually doing the solution you want. So it's, I can kind of show you in a bit more detail afterwards. It's kind of a bit weird. So we know how to calculate the bulk, the main part of the geometry. So all we have to do is add in the bit that comes from the bubble wall. And so this has two sort of contributions, because of course what we're doing is we're integrating the wall action itself and also the contribution to the integral of the Ricci scalar, which now has a delta function in it. So this is kind of coming from the wall plus sum of Ricci, and then the rest of it comes from sort of terms that are also hidden in Ricci. So this is the wall piece, and then if we now take the general bounce action, and so what I've done here is I've actually written it down in generality. So this is true whether or not it's de Sitter, anti-de Sitter, or flat on either side of the wall, whether or not there's a black hole on either side of the wall. So obviously anything outside the bubble will, if you're doing the bounce action, that they always any part of the action from outside always kind of cancels out. And so it's only really the difference between what the wall and its interior and what it replaced. So here, R plus is the black hole horizon radius from, that the outside people would think was the black hole radius, given their Riemann curvature. R minus is the actual remnant black hole radius on the inside of the bubble. This is this action of the wall here, the integral of the tension, times a sort of area term. Lambda is that proper affine time around the wall. And then this is the other piece. So everything, everything kind of drops out, and what you're left with is just integrating over the fundamental period of the wall there. So that's the sort of overall result. Now if we put Coleman Delizia in, we set the masses to 0, we put lambda plus and no lambda minus, we actually get the same result. So it's good that it works. And here's an example of what it looks like. If we just take specifically modifying Coleman Delizia, where we put a flat bubble inside Schwarzschild de Sitter, so this is where after tunneling there's no black hole. This is our classical potential. So the Euclidean solution is reverse, turn the potential upside down and look at classical solutions, kind of going from one turning point to the next. This would be our sort of pseudo-Friedmann equations, which look like particle motion in a potential. And if you notice that the general solution, so this was like the trig, the cosine sine. The general solution is, possibly periodic, but we have to find it numerically. But there's a very special solution here, just where the bubble's about to disappear, or the possibility of an instanton is going to disappear. And so there's kind of an unstable static solution with a specific radius that you can find, obviously. And so this is an example where we have no conical deficit, so we can cross-check again. We kept sort of getting obsessed with cross-checking that we were doing the right thing with the conical deficits. So here is another example where we're not forced to choose a periodicity, so we can tune it to make everything regular. And we find it's exactly the same whether or not, whatever our periodicity is. So this critical action is just the area of the black hole event horizon. And so here we plotted that as a ratio of the Coleman Delizia action. So you see that this, what we're kind of varying here, is the tension of the wall. And you can see that this ratio goes right back down to 0. So for a fixed wall tension, you've only got one possible static solution for one possible mass. So although we've plotted really mass on the bottom, this curve is labelled by, this mass would depend on the tension of the wall. So you can get as low as you like with the action if you have a very light wall. So you can scan through parameter space. So here we've set this tension parameter to be 0.2, and we've scanned through all possible parameter space to see what happens to the action. So if I can just try and illustrate here, there's this lower boundary here is the static solution. The upper boundary is kind of another sort of limiting process. It's really just looking at parameter space and seeing when the solutions disappear. This line here is where you get rid of the black hole, and then these lines are all where the interior is sort of, there is a black hole. Now the dotted line is where the remnant black hole has the same mass, but you can actually get to a situation where it's bigger on the inside, where you've got a black hole that's actually bigger after tunneling than before. But the thing to notice is that obviously the process that will happen at any given mass is the one with lowest action, because you exponentiate this to get the probability. So either you get rid of the black hole with a bubble, dynamical bubble, or you've got the static bubble and there's a remnant. So that's what that picture says. And so that's really saying this, everything I've just said. So a general instanton is going to have remnant black holes, seed black holes, and here I'm just kind of giving an idea of parameter space which changes according to the tension of the wall. Now with Coleman and Delizia there was an absolute cutoff of wall tension in sort of Planck and rescale Planck and de Sitter length scale of 0.5. But once you've got black holes, you can actually go to heavier walls, and then it cuts off at around 0.77 or something. So you can get much heavier wall, tunneling with heavier walls when you put in a black hole. And so here, this is sort of showing, this was the curve that I just had for sigma 0.2. This is 0.1, 0.3, 0.4. You've got the same sort of shape, but you see as you drop the wall tension, this gets steeper and steeper, and you go closer and closer to having almost zero action. I've got to lose my voice. So that's just plotting the remnant mass. So one of the things you might worry if you're getting down to very small mass black holes is what happens. Are they really going to nucleate vacuum decay, or are they just going to evaporate? So we tried to estimate this by looking at the evaporation rate for a black hole versus the tunneling rate for one of these static black holes. And what you see is that although you've got a nice prefactor here, it's actually not above the Planck mass, but for about, I think it's above 3 times the Planck mass, this ratio becomes less than unity. So it peaks at around just below Planck mass black holes at about 39. But clearly it's something to worry about. The fact that you need very, very, close to Planck scale black holes before before you can say that for sure the nucleation rate will actually beat evaporation. But of course, again, that assumes that there's nothing else going on. If there's anything around for the black hole to accrete, that will actually dominate. And so, it's kind of, again, one of these things where maybe it does, maybe it doesn't. It sort of depends on details. So what I wanted, this is just to give an idea. I've been asked by people what's the size of these things. So I kind of thought, right, what's the size? If sigma bar L, this parameter that I've been using, is 0.1, then what does that mean? This is sort of, well, sigma bar is the energy of the wall in Planck units, L is the scale of the false vacuum, and so your Coleman and Delizia action is looking like, sort of roughly speaking, looking like L squared on G. And so if your L was around Gauss scale, then this would give L squared on G of 10 to the 8 or 9. And so this gives you a Coleman and Delizia action of about 10 to the 6. So you'll see some of these numbers coming back later. Whereas the B star is, in this case, has dropped to 10 to the 4. So we've dropped the Coleman and Delizia action by 2 orders of magnitude. And if you look at the size of the bubble nucleated, it's a quarter of the size of the universe, and the critical mass is quite small on the other hand. So the horizon radius of the black hole is sort of down at, thousandth of the size of the universe. So, the nucleated bubbles are actually quite large. But that clearly is where everything's, 0.1, everything's sort of in the ballpark of Planck scale. So just to finish off, I just want to apply this to thinking about the standard model vacuum. So one of the curious things about, now that we know that the Higgs exists and we've got an idea of where its mass is that its mass lies in a really sort of tantalizing region, in that if you calculate the way that the Higgs coupling actually runs with scale, it's incredibly sensitive to the top quark mass, which is not that well known, so my colleagues tell me. And obviously if the Higgs mass put us in a region of instability, we'd be worried, because we'd think, well, that can't be. But it's actually put us in a region where it looks like the vacuum that we live in is not actually stable, it's only metastable. And so what it means is, sorry, I haven't got the plot of the speculator. So it looks like, you could get potentially one of these tunneling processes. So that's what I just want to just say a few words about, our most recent thoughts about this. So this is the sort of standard model bit, and this becomes negative at large phi, so large values of phi. But it's believed that there may be quantum gravity type corrections, which are at higher order. And so when phi becomes a Planck scale, these terms are potentially relevant. So it's really all about sort of sizes of extra terms. So we redid the analysis, putting in instead a flat outside and an anti-de Sitter inside. So we're just really taking the potential that we had before, and instead of having the lower one being 0, the upper one's now 0. So that's what we're modelling the Higgs vacuum by. And the only real difference is that this dip is sharper for lower tension. So it's very similar, just a bit sharper. So to think about Hawking evaporation, we actually thought about charging up our black holes, because if you charge a black hole, you drop its temperature, so you can lower the evaporation rate, but you don't actually change the tunneling rate very much. So I think I've put, this sort of gives you you can see this is the same sort of picture coming up. So this is a different amounts of, in this case, monopole charge. You've got the same shape plot. So what this here is meant to represent is, what we're plotting here is the ratio of the sort of critical decay rate, the static bubble, the lowest possible action decay, to the evaporation rate, as kind of ratios of your sort of critical mass. And so you see that it's actually quite possible, even at fairly low initial values of charge, to get above the evaporation rate. So we have checked that this makes sense. So how do we apply it to the Higgs potential? Well, we're still running the numbers a bit with this, but so here's sort of some of those potentials that I mentioned, that plotted. And what you see is there's an initial barrier, then there's a dip. And if you kind of put this potential and solve it exactly for in field theory, you see that you get something that looks like a kink, that's what a wall looks like, with quite strongly localized energy density. And so it looks plausible to use a thin wall approximation. So for a thin wall approximation, roughly speaking, the height of the potential barrier should be bigger than the dip of the false vacuum. And this is just for further reference. We've also got, the fact that the Higgs minimum is way out somewhere at the sort of comparable to a Planck scale. So G measures how close the minimum is to the Planck scale. So here's a table of what we get if we put a thin wall approximation and use our critical instanton. So here, this is the critical mass, which is approximately dependent on the cube of the tension. So here's some numbers. So Philip ran the numbers for this, and I've just highlighted one that's sort of promising. So what's going on here? This is lambda star. So this is these are the parameters in the that are the sort of standard model parameters. So this is sort of things. The range of lambda star and phi star are known. So we've kind of looked at numbers that are in those ranges. Lambda 6, on the other hand, is kind of fair game. This is the quantum gravity correction. Here's this G. So here we're looking at something which is perhaps sort of above gut scale, but only a couple of, not too much. And this is the ratio of the height of the barrier to the depth of the true vacuum, and that's got to be bigger than 1. So we're obviously pushing our limits here. This is the anti-de Sitter length scale, so that's huge. This is the tension. So what you see is the tension is really, really low, and this is the ratio of our critical mass to the Planck mass. So we want that to be above 1, and here it's not hugely above 1, but at least it's safely above 1. So in this case, the Coleman and Delizia action is at 10 to the 6. That was what I was saying before. But the critical bounce action that we've got is down at 30. So we've dropped more than 4 orders of magnitude on the Coleman and Delizia result, mainly because we've got a low tension. So we are pushing the bound. We're being a bit cheeky here about what you can do, but nonetheless it's a sort of proof of principle that you can, in principle, drop your tunneling decay rate. Of course, it's a very light black hole. So, whether or not it's really a sensible black hole is another matter. So, just to wrap up, I guess the key sort of technical point initially was dealing with conical deficits properly. Hiscock had actually looked at this problem in the 80s, but he'd assumed the conical deficit had a negligible contribution to the action, and that's not really the case. So we've kind of tested it, for known cases, and it gives sensible results. We've shown that a tunneling amplitude is significantly enhanced in the presence of a black hole, and it seems as if evaporation does beat tunneling in pure de Sitter, but it's not obvious. But I'm strongly betting that in a slow roll background that will not be the case. But the other thing that we realized is, because this is a gravitational result, if we were somehow able to build a star instead of a black hole, so some static configuration, then there would be no event horizon, and so no sort of area over G sitting in the bounce action. So we suspect, that the amplitude would be enhanced even more. So that's sort of a bit of an open question. And, we can sort of apply this to Higgs vacuum decay, but, at least if you're just in 4 dimensions, it would seem to need primordial black holes. But of course, I suppose if we allow ourselves extra dimensions, and we could have an LHC black hole do it. But anyway, that's what I wanted to say.
Thanks very much, Ruth. Questions?
So this final point, am I right in understanding you're saying in the presence of primordial black holes we could enhance the decay rate?
Yeah.
Of the Higgs vacuum. So can I turn this on its head and say the fact we're here means there's very primordial?
Yes. Yeah. But then I think there are other bounds on primordial black holes that might be stronger. But what we're trying to do is to check properly what the effective charge is, because then, at the moment we're still at the point where we suspect that the black hole would have evaporated. So that's why we kind of want to be sure about charge. And I think the other obvious place where this could again possibly be relevant is, with the cross sections for producing small black holes at LHC. So, but that's a whole new can of worms.
On your
Yeah.
The left-hand side of that plot was a universe that did have a black hole tying into a universe that doesn't.
So, well, I mean, actually, any of them. In this case, so on this side, this part, the initial drop, that's where you tunnel, you get rid of your black hole. No, wait a minute, no, that, yeah. In this case, we get rid of the black hole. Sorry, I was just hesitating because if you have a charged black hole, you can't. You've always got a minimum. You tunnel to the extremal case because you tunnel to the lowest mass. So on this side, you've got no black hole left. On this side, there's a remnant.
Is there any way of, I mean, I know we don't really understand the information of black holes anyway, but is there any way of understanding what happened to the information that was in the black hole?
Was in the black hole.
There anymore?
No, actually, Misao Sasaki's been sort of playing with this idea in terms of, as part of, exploring an information paradox in the sense of, saying that, perhaps, as you say, the black holes disappeared, but I think he was actually thinking more about maybe that either the information was never there or you somehow get it back. I'm not entirely sure. But yeah, I know he's certainly been, it's intriguing anyway, there's a recent paper by him.
Other questions? I have one. At the very last slide, it just said something about replacing the black hole with something like a star. And I'm not sure I fully understand that. I mean, part of the whole thing, you can describe everything purely geometrically.
Yeah, so really there were two ways that we computed the amplitude. So I gave one way, which is like the classical relativist's argument, in the sense of computing a gravitational action with Israel junction conditions and just directly calculating it. Another argument that we also put in the paper, which was sort of more Ian's way, was an actual canonical decomposition, so sort of 3+1 type of decomposition. Now in that case, so the geometrical way will deal with time dependence. So the 3+1 needs your background to be static, but in that case what you see is no matter what you've got there, what configuration of your scalar fields, as long as it's static, everything falls out and all you get are the area of the horizons. So
the matter will not need to be...
The matter doesn't give you any contribution to the bound. So that's why I said that if there's no event horizon, if you have some static sort of knot or something of scalar field, then it's got an even lower action because there's no event horizon. So that it's coming from that. It's coming from this other way of doing the calculation.